Hey everyone, today we're going to continue with our vector addition that we started last time. So last time what we did is we said that one way that we can add vectors is using what we call the tip-to-tail method, which is basically a way of taking two vectors, like let's say this and that, and you redraw one of them, and then you can draw in a resultant. And basically what that does for us is it tells us kind of what the resultant looks like. Right, it would point directly to the right, it has some kind of length, but it's not super mathematical. So today what we'll look at is how could you actually take those two individual vectors and calculate the resultant. Give it a magnitude and a direction. It's not super complicated, but it is kind of like a tedious process. So we'll walk through it, we'll be okay. Now the most important idea here is we're going to keep our directions separate for this. And when I say directions, I mean like our components. Remember when we first did vectors, we said that they have you can have like a north component and an east component, or like a horizontal component and a vertical component. We're going to be dealing with something sort of very similar, but for today, well, let's just call it the x component and the y component, where everything x is horizontal and everything y is vertical. So to calculate the resultant of two vectors, what we do here is we add the components separately. And that's sort of the most important idea here, is we have to find the components of the two vectors, the x components and the y components. We'll add those individually, and then we can recombine them at the end using a Pythagorean theorem. This is definitely one of those things that's easier to show you than it is to explain. So let's just dive right into an example, and I'll keep coming back to what I set up here. That way we have so you can kind of see what I mean by that. So let's take two vectors. The diagram below represents two force vectors. Let's call it force A and force B. So we've got two vectors act on an object located at the origin as shown. So our object's just going to be like right here, right at the origin. Each box represents 1 Newton of force. Okay, so each box just represents 1. What is the x component of vector A? So we did components already. This should be a familiar sort of exercise here. X is going to, again, represent that across the x-axis in your math classes. So A goes like up to here. So I've got that horizontal component, that x component as being 5. I'm just going to leave out the units for now, just to kind of simplify a little bit less writing. I have my less good stylus today, so I'm having trouble writing. What is the x component of vector B? So vector B goes, again, that's this one right here. I'm just going to kind of draw it down, and it looks like it goes to the left. So I'm going to make this x component negative, so I'm going to call it negative 10. Yeah, and that's it. Now, what is the total x component of the two vectors? So when I say that we add the components separately, this is what I mean. We have the x components of the two different vectors, and we're just going to combine them. Plus 5 minus 10, I think that's a total of negative 5. So our resultant vector, the combined effect of these two when we add them together, will have a horizontal component of negative 5. So let's talk about the y components. What's the y component of vector A? Okay, vector A is here. I think it looks like it's 6. Whoops. Oh, goodness. That's a 6. What is the y component of vector B? So vector B is here, and I don't think I have to really draw across here, right? We can see that it's 1, 2. It has a value of 2. So what's the total y component of the two vectors? All right, well, plus 6 plus 2 is 8. And that's really all the tools that we need to calculate or to find the resultant. The resultant has a total, when we combine them, the resultant has an x component of negative 5 and a y component of positive 8. Okay, we just found the two x's, found the two y's, and combined them individually. So that resultant, let's draw that in right now, and should go, again, have a x component of negative 5, so it'll go across to negative 5, and then it has a y component of positive 8, so that's 1, 2, 3, 4, 5, 6, 7, 8. So those are the two components, and the resultant goes directly from start to finish. I'm not going to dot it because I can't do a good job with that. There we go. And let's give it an arrowhead because it's a vector. That is our resultant. And again, we got that just by combining the two x's, the two y's, and doing that. Now, last time I told you something like totally different. I told you we can do this tip to tail, which means we draw one and then the other. So let's actually take a moment to like kind of see what we would have gotten if we did that. So for G, carefully, emphasis on carefully, draw the vectors tip to tail and draw in the resultant force, which we'll label R. Okay, so that's exactly what I'm going to do. Let's pick one to redraw. I'm going to redraw A because, I don't know, it just looks like it's shorter. I feel like I'll mess it up less. Okay, A looks like, again, we have to redraw it perfectly. So just as much across, just as much up. It looks like it goes like 5 across, 6 up. So if I started here, and again, I have to redraw A like perfectly. It has to go like 1, 2, 3, 4, 5 across, and 1, 3, 4, 5, 6 up. So I'm just going to redraw it. Let's do a different color here. This is vector A. Oh, no, I messed that up. This is our vector A. No, come on. Vector A. And again, I carefully redrew it on the grid. And I really apologize for the stylus situation right here. And I ended up right here. Again, A, it's a little crooked, but you can see that these are like supposed to be the exact same arrows, roughly the same, exactly the same length, exactly the same direction. And something kind of neat is, notice that when we did our component method and we drew in the resultant, and then when we do their tip to tail method and draw the resultant from start to finish, you see how we ended up at the same place? So the tip to tail method is, it's a great way of drawing this. The component method is just a little more specific here because we were able to like come up with numbers for all of these things. And if we talk about our resultant force again, so I'm just going to talk about this arrow right here. What is the y component of that resultant force? So I'm just gonna, let's change color one more time. I'm just gonna kind of look at this. The y component is, again, I'm just going over here. It looks like it's 5, 6, 7, 8. So the y component is 8. What is the x component? So if I draw it down, looks like the x component is -5. And the thing to point out here is how that perfectly matches our answers to C and F, those two individual components. So when we do the tip to tail method and we end up at this particular place, it's the same as adding the two components individually. That's our process. That's what we do. We find the two x's, we find the two y's, we add those together, and those are the components of our resultant. But how big is the resultant? Like this, we know the components, which is cool, it's helpful. But this R, like again, this arrow right here, how on earth could we find it? How could we find the magnitude of this resultant force? I'm hoping you're looking at this, and if you remember our, vectors unit at all, you remember there are like a lot of triangles in it. And I'm looking at this resultant, and I'm just going to overlay another triangle in a different color just to make it look, pop out maybe a little bit. See this triangle right here? We can do some trig with that. Or in this case, we can do Pythagorean theorem. To find the magnitude of that resultant, you can do a squared plus b squared equals c squared. I'm not going to show all my work because I do want to keep this video kind of short-ish. It's your guys' weekend, so I don't want to take up all your time. With those two legs of the triangles then would be the x component and the y component, which we found before have values of 8 and 5. 8 squared plus, I'm going to make it -5, but since we're squaring it, that negative is going to drop out anyway. And then you get a resultant of C is equal to, I got a result with magnitude, 9.43. And I'm hoping if you do that on your own, that's exactly what you'll get. Cool, so we did the math for it. And again, what that boiled down to was find the x's, find the y's, combine them individually, and those are our two components. Which, when you look at the geometry, you end up with this nice right triangle. So for the sake of time, we're going to skip all these direction ones. We'll do them in class when we get a chance, so we're not going to worry about that. But quickly, for the direction, basically what you're looking at is sort of a trig problem, right? We've got this angle in here that you can do the math for using tangent. But again, let's just kind of move the video along so I don't keep you here forever. Okay, so let's say we have 4 vectors that we wanted to add. Like, what do we do then? Well, it's like adding 4 numbers, and in fact, that's literally what it is. We're going to do the same process, but we've just got 4 values instead. Keep yourself organized when you do this. So here's what we're going to do. We are going to find the magnitude of the vector sum of these 4 vectors. Again, we'll worry about the direction stuff some other time. If you think you got a handle on this, pause the video and try it on your own. If you're a little nervous about it, I'm going to go over in a second, so don't worry about it. Okay, so if you tried it on your own, that's great. If you just want to follow along, also cool. So to find the magnitude of the vector sum, again, this just means we're going to add all the different vectors together, and our process, quite simply, in the simplest, one sentence form I can put it in, is we're going to add the components separately, and at the end, we can recombine them. So let's do this. Let's figure out all of our components here. We've got we've got an X component for A, we've got an X component for B, we've got an X component for C, and we've got an X component for D. Okay, so for A, our X component is, I've got -2 for A, right? Because it goes backwards by 2 for A. So A equals -2. This is sloppy. For B, I've got an X component of +2, because again, it just goes, how far along the X-axis does it go? 2. For C, I've got an X value of -1. And for D, I've got an X value of +3. Combine all of those together, and our resultant, I'm just going to call it R, because why not? The X component of our resultant, of our total is, I've got -2 + 2, -1 + 3 is, I think, +2. Let's change colors for our Y direction, because again, we do all of these things separately. The Y component of A is, I've got +3, because that's how far up it goes. The Y component of B is, I think -2, because that's how far down it goes. The Y component of C is, that's right on the axis. It doesn't go up or down, so I'm going to call it 0. And the Y component of D is, I've got +1. Add all of those together and we get, okay, +3 - 2, we got 0, and then plus another 1. I think that's +2. And again, that is the resultant's Y component. So let's fit all this together here. Let's see if we can figure out what, what this is actually going to look like. So our resultant, what do we know about it? We know it has an X component, or it's going to go across with a value of +2, and we know it's going to go upwards with a value of +2. That's our X component across and our Y component up and down. Drawing in the resultant goes from start to finish, and let's give it an R. Right, R for resultant. Awesome, that's it. But that's not the magnitude, that's just our 2 components, so I guess that wasn't it. Whoops, almost out of battery. So, how do we calculate the magnitude of the resultant? Well, I'm looking at a right triangle, right? Those 2 blue sides are the legs of our triangle. I'm talking about this and this. And we can just calculate that hypotenuse. So, let's go. Let's try that out here. A squared plus B squared equals C squared. 2 squared plus 2 squared equals C squared. And again, I'm just getting that 2 from 2 and 2. Okay, 2 plus, I believe that's 8 equals C squared. The square root of 8 is, I did this ahead of time, I got 2.83. Equals C. And I'm just going to go unitless here. Sorry, let's just put it C equals. There we go. Awesome. So again, just to recap, what did I do? I found all the X components, I found all the Y components, I did those separate, then combined at the end. Okay, so how bad do these actually get? Well, they get something like number 12, which is, again, about as bad as I could possibly ask. The diagram below represents 2 vectors that act on an object. So we've got 2 vectors. Vector A has a magnitude of 6.9 and is kind of below the x-axis at this angle of 54 degrees. Vector B is, has a value of 13.4 and is above the axis at this angle of 43. So if we tip to tail them, we get, like, I'm going to redraw A at the end of B. I tried to keep the same length. I didn't do a good job of it, but that's okay. And then we draw a resultant. It would look something like this. Clearly, that's not very scientific. So what we're going to do is we're going to calculate the value of that resultant. And I tried to break it down for you. Okay, our process for this is we find the x components, we find the y components, and then we go. Now, I didn't give you a nice little grid here, but we learned at the beginning of the year the reason we invested some time in calculating those components is, well, basically exactly for this. So let's kind of draw these out, and I'll do the math on the side. I got to zoom in a lot so I can sort of fit all my writing in, so I'm sorry if it's a little hard to follow. So for the A, we've got this x component and this y component. So remember our SOHCAHTOA? Alright, from the beginning of the year. To find, let's do the x first. Find the x component. That looks like it's going to be, again, this is our 54. I know I zoomed in so much that looks like the 54 is in the middle of the triangle. But that's our 54 degrees. So I want that x component, which I think is adjacent, and we know the result, the total magnitude there, which is the hypotenuse. I think that's going to be cosine. So what I'm going to do, and I tried to lead you along here, solve for the magnitude of the x components of each of the two vectors. So for that x component for A, what we can do is x is equal to, and we said it's going to be cosine. I'm going to do a little bit of the algebra, so almost I'm not really going to show it all. Is the total value of A, which is 6.9. Let's clean this up a little bit. Times sine. Oops, I'm sorry. We agreed it was cosine. Cosine. I apologize. Times cosine of 54. Make sure you're in degree mode in your calculator, and you should get a value of 4.06. And as long as we're talking about A, I'm going to actually find the y component down here, because I asked for it anyway, and we're going to need it at some point. So the y component, if you go back to the triangle, looks like it's not going to be cosine, but it's going to be sine. So 6.9 times sine of 54. And that gave me a value of, when I did it, I got negative 5.58. Now you might be wondering where that negative came from, because I didn't mention a negative. This, if you plug it in your calculator, would not give you a negative. And basically what I'm saying is, look at that y component for A. Like, would you agree that it's downwards in the negative y direction? I would say so. So I just made it negative, because we know it should be downwards. Okay, now for B, I'm going to do the x and y, and I'm going to sort of fill them in parts A and B over to the left. So for this, so for vector B, it's got this x component and a y component. This is our 43 degrees. So let's figure out the sine and cosine now. For that x component, this looks like it's adjacent. So I think for that x component, we're going to use cosine, and for the y component, this is opposite. We're going to do sine. So again, it's just, basic trig like we did at the start of the year. So for B, the x component, again, for the x component, we said we're going to do cosine. So we're going to do 13.4 times cosine of 43. And when you do that, you get a value of, I got 9.8. And then for the y component, it's 13.4, and we agreed before that that should be sine of 43. And when I did that, I got 9.13. Okay, cool. So why did we do that? Again, we separate the components. That's the process. And then we combine the components, and then we talk about our result. So let's combine them. Let's do red for the resultant. Oh, that's not red. Is that red? I'm actually colorblind, so I have trouble with this. Okay, so I'm going to combine these two, 4.06 and 9.8. What do those make? You just add them together. 4.06 plus 9.8. Do that in your calculator or in your head. I got 13.86. And again, that is the resultant's x component. For the y component, I'm sorry, negative 5.58 with 9.13, combine those two, and I got 3.55. And that is the resultant's y component. Let's draw those in and see what our resultant looks like. So I'm going to clean up my diagram here. I'm just going to, erase everything, basically. And remember before with that resultant, it kind of like cut through across the middle-ish of the two? This one hopefully should as well when we do it. So again, we got 13.86, which is kind of far to the right. Just looking at the other values, which are like 6 and 13. And 3.55 is not super high up. So I think it's like that. And then our resultant goes from start to finish. Again, these are the components, the x part of it and the y part of it. Let's give that R for resultant. And the last thing we need to do is solve for the magnitude of that. Well, we have a way of doing that because we know that these two components are 13.86 and 3.55, and we have a right triangle, which we love in physics because it lets us do Pythagorean theorem. Okay, 13.86 squared plus 3.55 squared equals c squared, and you get c is equal to, I'm just going to kind of jump to the end there, 14.3, the magnitude of the resultant. Notice that that kind of matches our tip to tail that we like started out with when we tried to imagine what it would look like, right? If you redrew A at the end of B, you kind of end up there. So this, as far as tip to tail goes, this seems like a good fit. This mathematically described part, again, we're not going to worry about the directions here. If I did ask for the direction, see this angle right in here? Just use tangent to find it. Again, we'll do that in class. Okay, here's what we're going to do. Let's have you try one on your own where we just totally take the training wheels off. So for 13, just add the 2. And again, let's skip the direction here. I would like you to find the magnitude of the resultant vector. Pause this, try it on your own. I'm going to go over it in a second. You may want to go halfway through my explanation, kind of make sure you're on the right track, so that way you don't, because this is going to take a little while. And then see how you're doing. So again, pause this, try this on your own, see what you can do. If you're totally lost, that's cool. I'm going to go over in a second. Alright, 2 vectors shown, x concurrently on an object. Find the magnitude of the resultant vector. Let's go. Again, if you tip to tailed it, draw B at the end of A, the resultant should look something like that. Kind of like through the middle of these two. Let's see if we can get that mathematically. Whoops. So the first thing we do, again, we have to split it into components. That's the important part here. So let's do x components first. Ax is equal to. All right, we got to figure out sine or cosine, right? Because it's always going to be the trick to find the components. And draw this across. Now the 23 is meant to represent this angle in here. Okay, so this x component, which remember is the across component, it looks like it's opposite the angle. Sine is opposite over hypotenuse. So for our x component, it's going to be 6.3 times sine of 23. And I got 2.46. But be really careful here. You see how that x direction is like, to the left-hand side? It's in the negative direction. I'm going to make that negative because, again, that x component is pointing towards the left. Let's make this more clear that it's an x. Okay, now let's do the x component of b. So, all right, so for vector b here, again, we've got, it goes kind of like this. That's the x component. I'm going to draw it down so we've got our nice triangle here. Okay, so we've got, again, a resultant of 5.7. We've got this as our 34. I think that x component looks like it's adjacent, which means it's going to be cosine. So I'm just going to write sine. And we said that this is sine, which makes this one cosine when we get to that y. Okay, so again, let's just kind of write that in. It's what was the total value for B? 5.7. So for the x component, it's 5.7 times cosine of 34. Make sure you're in degree mode. I got a value for that of 4.73. Okay, which means that our total x component for our resultant is 4.73 negative 2.46. I got a value of 2.27. Cool, awesome. We're halfway done, right? We did one of the components. Now let's talk y component, and we're going to do that in this color. It's like green. Y. Let's go. So for A, the y component is, alright, that's this guy right here. Looks like it's adjacent to the angle, so I'm going to do cosine. 6.3 cosine of 23. And when you do that, it looks like this is sort of, it's going to be close to the 6.3, because see how it's so much longer than the x component? And I got 5, oh, no. I got 5.8 when I did that, which, again, is bigger than the x component, which is kind of what that triangle looks like it's going to be. 5.8. Okay, and then by is, let's pull this up here. By is, again, that's this guy right here. It looks like it's going to be sine, because it's on the opposite side of the triangle as the 34. And when you do 5.7 times sine of 34, what do you get there? Should be about half, maybe a little more. I got 3.18. It's kind of better like 3.19 is where I rounded it to. You might have rounded differently, and that's okay, as long as you're near me. Which means that the y component is, alright, we've got our two individual y components, 2.27 plus, I'm sorry, whoops, I'm looking at the wrong thing here. 5.8 plus, that's a decimal, 5.8 plus 3.19, what is that? I think that's, I got 8.99. Okay, we're almost there. We've got our two components. Now we just need the magnitude of the resultant. So let's draw out our resultant here. Let's go with this color, orange. So the x component is 2.27, which isn't huge. So I'm just gonna clean up some of this. The x component 2.27, not huge. So I'm gonna draw it like in the positive x direction, but like just a little bit. So let's go like that far. And then in the y direction, we've got 8.99, which is going to be like, I don't know, longer than that. So let's go, oh god, like that. It's kind of big, so I may try to make it bigger than the other two, but I did run out of room on my screen. Okay, cool. It's not beautiful, but, and then our resultant goes from start to finish. And again, I know I didn't, yeah, okay. And if I was any good at this, our tip to tail would kind of end up in roughly that direction. But I think I did a terrible, terrible job drawing this, which I apologize for. Okay, so to find that resultant, we've got a right triangle. Again, it's terribly drawn, but it is a right triangle. Which means we can do, to find that resultant, a squared plus b squared equals c squared. A is, okay, again, our two components are the 2.27 and the 8.99 that we found down here. So 2.27 squared plus 8.99 squared equals c squared. I got c is equal to, I got 9.27. Okay. If that was rough, it's because this is a little hard. The component method doesn't really show up on the AP exam, but it's just like one of those things that you really shouldn't go through a physics course without at least covering it like a little bit. So anyway, that's that. So again, if it's tough, that's okay. We're only really going to use small parts of this, and primarily it's this component idea when we get to forces. For now, I want you to close out with two different problems, 14 and 15. Take a look at both of them. It's more like conceptual, so there's no math. So if you hated that, then these should go okay. Take a minute, try both of them. I'm going to go over them in a second. I'll give you a second to pause the video and try them on your own. Okay, 3 seconds. Sorry. Yikes. 3 students are discussing the magnitude of the resultant of the addition of the vectors. A and B. There's some grammar there. Vector A has a magnitude of 5 centimeters. Vector B has a magnitude of 3 centimeters. All right, so these kids are all talking. Justin says we'd have to know the directions of the vectors to know how big the resultant's going to be. Bilal says, since we are only asked about the magnitude, we don't have to worry about the directions. The magnitude is just the size. So, to find the magnitude of the resultant, we just add the sizes, and the resultant is 8. Sai says, no, these are vectors. Sai spelled vectors wrong. And to find the magnitude, you have to use the Pythagorean theorem. In this case, the magnitude is the square root of 34, a little less than 6 centimeters. Sakshi says the resultant is the vector that you have to add to the first vector to get the second one. In this case, the resultant is 2. Who do you agree with? Okay, any of them, all of them, what do you think? I'm hoping you agreed with Justin, and only Justin. We have to know the direction the vectors are in order to see how big the resultant's going to be. I'm not going to write out the reasoning. I'm just going to sort of explain it, and I want you to see if you can find your own words for it. The idea is that, actually I'll use pictures to help out, which you can use, and that would be fine. To know that, let's pick some of the simplest examples. We've got 3 and 5, right? So imagine you had 3 and 5 in the same direction. Again, that's 3 and 5 in the same direction. That would give you a total of 8. Now imagine you had 3 and 5 in opposite directions. What would that give you? 3 and 5. Well, then they'd subtract from one another, and you'd get 2. Clearly the direction matters. So Justin's right in that sense. So we don't even have to dive into the trig. We don't have to make it that crazy. Use the simplest examples you can think about. You can't just add them, because, again, we just said that if they're in opposite directions, they would take away. If they're at angles, you got to do trig. So that's why Bilal isn't correct. For Sai, he says you have to use the Pythagorean theorem. Did you have to use the Pythagorean theorem? No, we just came up with examples where you didn't. If they were at 90 degrees from one another, you could use the Pythagorean theorem. But, again, we just thought of some examples where you don't have to. And for Sakshi, I think Sakshi subtracted the 2 vectors to figure out, to get this 2. But again, the angle matters, so that's why Justin was correct. Last up, 2 vectors have a magnitude of 6 units, which makes a small angle, alpha, just different from theta, but it just means an angle, with the horizontal is shown. 4 students are discussing the resultant vector obtained by adding these 2 vectors. Okay. Vector A has a magnitude of 5... Oops. No, lose this. This is wrong. Sorry. They both have magnitudes of 6, as illustrated here. That was copied and pasted from the previous question. So who do we agree with? Anna, since these are vectors, we need to use the Pythagorean theorem to find the magnitude. In this case, the magnitude will be the square root of 72. The direction will be downwards. Let's go one at a time, and we'll kind of figure out what's wrong, what's right with all of these. So for Anna, these are vectors. We need to use the Pythagorean theorem. The square root of 72 comes from doing like 6 squared plus 6 squared, right? Okay, we definitely did a thing with Pythagorean theorem in it, so it feels like this might be a good idea, but this is not the correct way to do it. And the reason for that is, remember our process. It's to separate the directions, and then once you've combined, the x directions and the y directions, you go from there. I think Anna forgot to separate the 2 directions, meaning, she didn't separate the 6 into the horizontal and the vertical components, and then do the math from there. So I know the Pythagorean theorem is oh, that sounds familiar, but we didn't do the full analysis there. For since these are vectors, we have to find a direction and a magnitude. We use the vectors to determine the direction, which is down, but to get the magnitude, we just add them. The magnitude of the resultant is 12. Well, let's see what we got here. So Barinder says the direction is going to be down, and you can just use the vectors to figure that out. And he's kind of right, because if we just do these tip to tail, I'm going to redraw one at the end of the other, and you've got a resultant that is downwards. So this is our resultant. And I just use the tip to tail for that. I'm not even doing any math. Cool. It seems like a good idea. He's kind of right? The direction is down, but you can't just add 6 and 6 to get 12. Because, just kind of looking at this resultant looks like it's going to be kind of small compared to the 2 6s. So he's on the right track, but Ricky says, I think the direction's actually up. The resultant should add these vectors to get to 0, and since the 2 point down, we need something to point up. No, Ricky's just off base. Patrick says the magnitude will be less than 6. Each of these points down just a little, so the resultant will be pretty small. I think that sounds good, right? When we drew this out, see how this resultant's kind of smallish? And it does point downwards, so Patrick's going to be correct on this one. He's the one I would agree with. The reason the resultant becomes small, for a couple of reasons, is one, if you draw the tip to tail, it looks very small. But another reason is if we think about our x components here, we've got a positive x component, a negative x component, and it looks like those two are going to cancel out, right? Imagine giving these numbers like plus 8 and minus 8. Well, those would cancel out to make 0. So basically, all of the x components of these vectors are canceling each other out, and we're just left with this downwards y component. So if you're explaining your reasoning, if you put anything along those lines, that works. Okay, that's it for this. So again, that component method, I know it's tough. I know there's a lot going on. It's not real, it's not something we're going to do a whole lot with, but it's definitely one of those things where, as a physics teacher, you should see this at least once in an AP level physics course.